In this video, we're going to look at lesson 8.4, which deals with sigma notation with series. So really, it's going to take everything that we've dealt with so far, arithmetic series, geometric series, and infinite geometric series, and we're going to learn shorthand, because that's really what sigma notation is. We have the Greek letter sigma, and so the Greek letter sigma is shorthand for the word sum. So when you see sigma, you need to think that you are finding the sum of what's next to it. And so here is a visual, analyzation of sigma notation. And so you have the Greek letter sigma. You're going to have an expression, well, an equation below it, n equals some number. And in this case, I just have n equals 1. That is the first value of n. It's the first position in the series. It's the position that you are starting at. It's your first input into the expression. The number on top, so I just have a k here. This is going to be some number. That's your last value of n. And so this is where you are stopping in this series, what the term position you are stopping at, while the bottom is the term position you are starting at. And then to the right of sigma notation is the formula for the series. And the formula is just the equation for an arithmetic sequence or a geometric series. It's those concepts you learn from 8.1 and 8.2. So the number on the bottom is where you're starting. The number on the top is the position you're stopping at. The expression to the right of sigma is what you're plugging into. Here is an example, just so we can get used to the structure and kind of how we're going to lay it out, is right here I have the expression 7n minus 11. So I'll keep the same color coding. There's the blue. The position number I am starting at position 1. So I'm going to use a table like we've done before for the series to organize it. So I have my position, I have the term at that position, and so we're going to start at position 1. And what happens, we're going to count up to position 2, we're going to count up to position 3, and we're going to keep going until we reach this position. So my last input is going to be 12. So that kind of shows you the positions that you're going through for the series. Now we just need to find what are the values of it. And each of those n's is an input. So I am going to input 1 into the blue expression. So I have 7 times 1 minus 11. And that's going to give me negative 4. For a series, remember, it's the sum of a sequence. So I'm going to put a plus sign in between. And I'm going to do the same thing. This time I'm going to plug in 2. 7 times 2 minus 11. And I'm going to get 3. And I'm going to put a plus sign in between. And I'm going to do the same thing. 7 times 3 is the new input, so minus 11. And I'm going to get 10 plus dot, 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 plus. Now I'm stopping by plugging in the 12th position, finding what that number is. So 7 times 12 minus 11. In this case, that's 73. And so that is how we're going to list out our series from sigma notation. So sigma notation is really shorthand for that entire list. Negative 4 plus 3 plus 10 plus dot, dot, dot plus 73 on it. And the next part we're going to be asked is, well, how do I know if it's arithmetic, or how do I know if it's geometric? And that's really 8.1 and 8.2 on it. Now you could analyze and go through and look at, well, what's the pattern from left to right? Or I could look at the structure of my expression. And in this case, the structure of the expression for this is very similar to like mx plus b, slope-intercept form. And when it's similar to that, it's arithmetic. We could also review what we did before geometric. Geometric, is very similar to exponential form. A times a base to a power on it. So if it looks like that, it's going to be geometric. And so we're going to use a lot of our understandings from the previous lessons to help us out for this one. So we're doing this problem down here for part 1. We are expected to know 3 things. And even on your quiz over this, I can ask you any of these 3 things, and you're supposed to know how to do them. You're supposed to know how to write out the series from sigma notation. That's what that table is. But make sure you put the plus signs on the bottom as you go through on it. You're expected to find out whether it's arithmetic or geometric, and that's the structure that we learned in 8.1 and 8.2. And then actually now to find the sum after you know that. Again, that's 8.1 and 8.2. So the new idea is how to generate my series. That's the new idea. And then we're just going to review what we've dealt with before. So first off, let's write out the series. And I'm going to use the same color coding to be consistent. So purple on bottom, green on top, blue for the expression. So I'm going to have purple on bottom, I'm going to have the green on top, and I'm going to have the blue for the expression so I can be consistent on this. So first off is write out the series represented by the sigma notation. And I'm going to look at it as a table. I have my position, and I'm going to have the term at that position. Well, what position do I start at? It's telling me n equals 1, so I'm starting at position 1. And then I'm going to go to position 2. And then I'm going to go to position 3. Dot, dot, dot. And I'm going to stop at position 32, is what it tells me. I'm going to then use those as my inputs. I'm going to do 4 times 1 minus 7. And that's going to give me -3. Since it's a series, I put a plus sign. And I'm going to do 4 times 2 minus 7. And that's going to give me 1. That's a plus sign. I'm going to do 4 times 3 minus 7. That's a plus sign, so 5. Then dot, 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 plus. Now my last input is going to be 32. So 4 times 32 minus 7, which is 121. So that is the first question. Write out the series represented by the given sigma notation. This right here with the plus signs, all the way from the first term to the last term, this is your series written out. You are expected to know how to generate that. The second part is determine whether it is arithmetic or if it's geometric. I like to look at just the expression. This setup, 4n minus 7, if I write it as t of n equals 4n minus 7, this looks like slope-intercept form for us. And so what that allows me to do is it allows me to actually answer the question. This is going to be a slope-intercept form, so it's going to be an arithmetic series. And if I look at that slope-intercept form, I can see my common difference is 4. And look up above. I have 4 being added in between each one. So now I can use and find the actual sum. Sum of an arithmetic series is going to be n over 2 times a1 plus b sub n, that quantity. And notice we have everything we need. And I'm going to come to n at the end. I have my first term as -3, and I have my last term as 121. Well, where do I find my n? N is the number of terms in the series. So I'm starting at 1, and I'm going to 32. That's 32 terms. So 32 divided by 2 is 16. -3 plus 121 is 118. 16 times 118 is 1,888. And that is your sum. I answered all 3 parts. I wrote the series out. I determined whether it is arithmetic or geometric. So I state which type. And then the third expectation is, okay, now that you know it, find the sum. I look for 2. Number 2, again, we're going to look at purple on the bottom, green on the top, and then the expression for the series in blue. So first off, list out the series on it. So I have my position, and I have the term at that position. We are being told we are starting at position 1, that purple end value. We are then told, well, you're going to keep counting up position 2, position 3, dot, 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 and you are ending at the position at the top, the 7th position. And so what happens is I'm going to plug everything in. I'm going to take 48 times 3/4 to the first power. I'm going to plug in that 1. In that case, I get 36. Since this is a series, I got to put a plus sign, and I'm going to do the next one. I'm going to do 48 times 3/4 squared, and that would give me 27. And I'm going to do plus because it's a series, and now I'm going to do 48 3/4 to the n power. Now n is 3, so 48 times 3/4 cubed, well, that is 81. Let's keep the color coding. That is 81/4 plus dot, 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 plus. All right, let's do the last one. I'm going to do 48 3/4 to the 7th. Now that one's a little bit harder. That is going to give you, well, let's just use our calculator. We have 48 parentheses 3/4 parentheses to the 7th power. Now I'm going to show you this. You don't want the decimal. We need the exact number. So I have to hit math fraction and get it's 6,561 over 1,024. So 6,561 over 1,024. Now technically, I could have done that as soon as it got difficult. I could have done 48 parentheses 3/4 to the 3rd power, and then hit math fraction, and that would give me my 81/4 as well. Or I could realize the next part is there's your series written out, check, done, boom, right there. That 36 plus 27 plus 81/4 plus dot, 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 plus 65, 61 over 1,024. That is your series written out. The next part says, hey, state which type, which is actually pretty useful to know in the beginning. If you look at the equation, 48 times 3/4 to the end, it's very similar to geometric form because it's similar to exponential form. So this is a geometric series where you have a common ratio. R is 3/4. So I named the type of series as well, which, by the way, to go back, how could I have done this position a lot easier? Well, if it's geometric, if I see it's geometric right away, as I could take 36 times 3/4, that gives me 27. I could take 27 times 3/4, and that gives me 81/4. So it's extremely beneficial even before you start listing out the series to know whether it's arithmetic or geometric. Now that it's geometric, I can find the sum. The sum of a geometric series is a1 times the quantity 1 minus r to the n over 1 minus r. And I can start plugging everything in. And so I'm going to have my sum equals, first term is 36, parentheses 1 minus 3/4. Now that 7th power is inside the parentheses, over 1 minus 3/4. So if I simplify this, I'm going to keep the top as is. I don't want to do 3/4 to the 7th power. I'm just going to leave it alone. But the bottom, 1 minus 3/4, I mean, that's just 1/4. At that point, I am so going to go to the calculator. And that's the part you have to keep in mind is how do I use my calculator for this? I prefer to use the alpha y equals feature and get the fraction. And then I could type it in the exact way it appears. 36 parentheses, 1 minus. I can do 3/4 in a parentheses. And then the 7th power. Close it. So that looks like the top. And at the bottom, I can have 1 divided by 4 for 1/4. The nice thing about using this, if I type it in using that fraction feature, it is going to spit out the actual answer. We have 127,773 over 1,024. We want the exact answer, not the decimal of it. We want the exact fraction for it. If I type it in without that fraction feature, it's going to be a little bit more complicated. You're going to have to do it in parts to make it a little bit easier. You would do the 36 parentheses, 1 minus parentheses, 3/4 to the 7th power. You would find the top first, hit enter, divide by the bottom. So since that bottom is a fraction of 1/4, I'm going to divide by 1/4 in a parentheses, hit enter. Again, you're tempted to write down the decimal and be marked wrong. You're going to have to convert that to a fraction. You get the same one. To me, it's easier to learn that your alpha, green button, y equals, that first option is a fraction for you. And if you type it in with that, it will give you the fraction automatically. So there's your answer to number 2. Where we answered all 3 parts. We stated the series written out, we stated which type, and we found the sum of it. So let's look at number 3. Maybe I want to state the series right away on it. And if I look at this one, I can see I have a structure. I have 3/4 times 2 to the n. Now, between arithmetic and between geometric, this structure is very similar to a times b to the x. Y equals a times b to the x, which means this is a geometric series. So even based off the beginning, I could state whether I have an arithmetic or whether I have a geometric series. So I can answer that right away. Could I also tell me what the ratio is? My ratio is, what am I multiplying my base? So my ratio is going to be 2. That's really helpful because now when I create that table, I think it's purple on the bottom, we have green on the top, and we have blue for the expression. When I create my table for that, lets me see the series written out, because that's the other question. I'm going to start at position 1. I am then going to go to position 2, and then position 3, and then dot, dot, dot. It tells me I am stopping at position 9. So we answered the first part. We answered what type of series am I dealing with. We went out of order. Okay. So my first number I'm going to input is 1. So I'm going to do 3/4 times 2 to the first power, which in that case gives me 3/2. Since it's a series, every term is separated by a plus sign on it. But since I know right away it's geometric and I can see from that fact that my common ratio is 2, I could just multiply 3/2 by 2. I can multiply 3 by 2. And so a couple of those numbers are going to be a little bit easier to do. I don't have to do this input 3/4 times 2 squared, 3/4 times 2 cubed. But I do need to think about it for this one right here. I'm going to have 3/4 times 2 to the 9th power. In that case, then go to your calculator for it. Let's have, and I'm going to use alpha y equals so I get used to it. 3/4 parentheses 2, raise it to the 9th power, hit enter. I get 384. So now I have my series written out. I answered that part of the problem. The next says to find the sum. Well, I already know that this is a geometric series on it. And so I can find the sum by using the geometric series formula. Now I'm going to have some fun. There are 2 geometric series formulas on it for finding the sum. We did the first one up here on it for number 2. I'm going to do the other one here. And just notice I'll keep the same color coding on it as we did that in purple. So we have here my sum. The second sum formula for a geometric series is a1 minus a sub n r over 1 minus r. And I'm going to use this one just because, a little change isn't a bad thing. So I'm going to put in 3 halves for a1 minus 384 times 2 on the bottom, 1 minus 2. Well, between the top and the bottom's easy. I have -1. For the top, I'm going to have 3 halves. So parentheses 3 halves minus 384 parentheses 2. So on the top, I have -766.5. So -766.5. And really, that's just changing the sign. So it's a positive 766.5. And that is your sum on it. So I've answered all 3 parts to the prompt. I stated the type. I wrote out the series. I found the sum. And I'm going to do it in the same order here. Since I have purple on the bottom, I have green on top, and I have blue for my expression. And I'm going to analyze that expression first. That expression is very similar to y equals mx plus b. I mean, it really is t of n equals -6n plus 37. That structure tells me this is an arithmetic series. And based off of that, my common difference should be -6 on it, that slope. So there's your first, well, not the first, but there's your answer. What type of series? I'm dealing with arithmetic because I can look at it and see its slope-intercept form. Now I'm going to list out the series for it. So I'm going to look at like a table. I have my position, and I have the term at that position. We are being told we're starting at position 1. And we're then going to go to position 2, then position 3, then dot, dot, dot. It tells us we are stopping at position 65 for it. And then I'm just going to do the input. For the first term, -6 times 1 plus 37. And so that first term is 31. Now I can input, remember plus signs in between. I could input each time the n and get the expression, or I can realize this is going to be arithmetic. So I am subtracting 6 each time. So this would be 25, and this would be 19. For the last one, though, I will have to, because it's so far away, I will do -6 times 65 plus 37 and get -353. So it's asking us to write out the series. There it is, done. And asks us what's the type. It's arithmetic. We answer that first. Now it's asking us to find the sum. So the sum formula for an arithmetic series is n over 2 times a1 plus a sub n. So I have here, I put over 2. My first term is 31. The next term is 353. Now, what's my n? I'm starting at 1, and I'm going to 65. So in this case, that's 65. So that's going to give me 65 over 2 times -322, which is -10,465. And that is the sum of the arithmetic series. I answered the third part of the prompt. So that's really the structure on it. These all are, when I say the same, they're unique because they all start at n equals 1. If you look at these 2 problems, notice it's the same idea. We have here, if I look at the structure, purple on bottom, green on top, blue for the expression. And let's start with that expression like we did before, is in this case, t of n equals 4 times 2 to the n. That's very similar to y equals a times b dx, which means that this is a geometric series. And my base, my common ratio is 2. So I did answer that part. That's the same. And we want to find the sum of it. So I have my n, I add all the way across my term at that position. But here's where it's different. You are told now that you are starting at position 3. You are not starting at position 1. So here's where it changes a little bit. You start at 3, so I go to 4, I go to 5, dot, dot, dot. I still stop with that input event on it. So I'm going to then just start. I'm going to plug in 3, so 4 times 2 cubed. Well, 2 cubed is 8. 8 times 4 is 32. Remember, we have a series, so we're going to have plus signs in between each term. Now, I'm told this is geometric. Found that out right in the beginning. So I could just multiply by 2, multiply by 2. And I have to do it on this part. I actually have to do 4 times 2 to the 9th. And I could use the calculator for that and say it's 2048. So there's my list of the geometric series. So far, it looks like the only part that's different is that first part. What number are you starting at? N equals 3. So be very careful to look at that number every time. What about the sum? How did that change? Well, the sum of a geometric series, we have two formulas. I'm going to use this one, A1 times 1 minus R to the n over 1 minus R. So let's see, my first term is 32. My ratio is 2, so 1 minus 2. But what's my n? And in this case, we have to be careful on it. In this case, you are starting at 3 and ending at 9. So how many numbers are there from 3 to 9? And we have to include 3. Well, there's 6 numbers between 3 and 9. We have 4, 5, 6, 7, and 9, but we also have to realize we're counting 3. There is going to be, in this case, your n is 7 on it, because you have 3, 4, 5, 6, 7, 8, 9. Let me tally mark. 3, 4, 5, 6, 7, 8, 9. You have 7 terms from 3 to 9 when you are including 3. So my n is 7. I say that's different because before your n was always the number on top. And the reason why is because you started at 1 because you were just counting from 1. But now you're changing what you're counting from. And at the bottom I have 1 minus 2. So if I type in the top, 32, parentheses, 1 minus 2 to the 7th, remember the power is on the inside of the parentheses, I get negative 4,064. So I have my sum is negative 4,064. 1 minus 2 is negative 1. Divided by negative is just changing the sign. There's the third part done. So the harder part of this one is going to be determining where you're starting is going to change. So it's going to be finding how many total numbers you are dealing with in this series on it. And in this case, if I look at this, you have t of n equals 3 halves n plus 11. That's very similar to slope-intercept form, which tells me this is an arithmetic series with a common difference of 3 halves each time. So I'm going to have my table n, my term position, my value at that position, so my position and the term at that position. And then what am I starting at? Now I'm starting at 4. That's what this tells me. And I'm going to go to the 5th position. Then I'm going to go to the 6th position, dot, 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 and I'm going to stop at the 15th position. So now I plug them in. So let's put plus signs in between, boom, 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 dot, 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 because we're asked to list out the series. So I'm going to have 3 halves times 4 plus 11. And that's going to give me 17. Now 3/2 is 1.5, so that's not too bad to add each time to get the first few terms. To get that last term, I'm going to do 3/2 times 15 plus 11. And that's going to give me 33.5. And so we have our first part is what type. We then have write out the series. Since this is arithmetic, I'm going to use my arithmetic series formula. Which says sum is going to be your n divided by 2 times your first term plus your last term. And there's a reason why on the first few problems I just went right to here and I left that n alone, is you have to realize sometimes your n changes. I am starting at the fourth term. I'm not starting at the first term. So how many numbers are there from 4 to 15? And that means you are including 4 from 4 to 15. And in that case, there are 12 numbers. I mean, look at this. We have 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Boom. There are 12 numbers there on it. So n is 12. So 12 divided by 2 I can do. That's not bad. I'm going to have 6 times 50.5, which isn't too bad. It's 303, and there is your sum. We answer the last part. So these two problems, be very careful on. Your starting position changed on it. So we took our numbers and we looked at, well, how many numbers from 3 to 9, and from 3 means you are including 3 in it, and there's 7 numbers on it. How many numbers from 4 to 15? Well, there's 11 between them, and then you have to include that 4, which makes it 12. Now for an infinite geometric series on it, the only difference is if I look at this one, you still have the same structure. You're told it's geometric, which is nice. So I believe we did purple on the bottom, we did green on top, and we did blue for the expression for it. The difference is you're not stopping. You are going to infinity for this. It is going on forever for it. Now I'm going to make a note. I know it's geometric, but I'm going to also make one statement. I'm going to state my ratio is 4/5 on it. That's just being raised to the power. So we're going to use 4/5 as the ratio, and I'm going to create the table just like we did before. So I have my position, term position, and then I'm going to have the value at that term position. We are starting at, it does say 1, that's helpful. Then I'm going to go to position 2, position 3, and I'm just going to go dot, dot, dot. There is no ending. It's going on forever. So I'm going to leave like that. And I'm going to put plus signs in between for the terms, dot, 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 because it's asking me to write out the series. Be sure you can do those. So the first term, I'm going to plug in 1. So I have 18 times 4/5 to the first power on it. And if I do 18 times 4/5 to the first power, I'm going to get 72 fifths. Now here's where I like to use this idea of the ratio up here. Is when you're multiplying fractions, you just multiply the top and you multiply the bottom. So I'm going to take 72 times 4, and that's going to give me 288. And I'm going to take 5 times 5, which is 25. I'm then going to take that 288, the top, and I'm going to multiply that by 4, and that's going to give me 1,152. I'm going to take the bottom and I'm going to multiply it by 5, and that's going to give me 125. So it's nice to know either what your ratio is or what your common difference is before you start the problem to help you generate the list. Otherwise, you're going to have to plug them in each time for it. So we did answer the first part, which is to write out the series. Done. Now we're asked to find the sum. So we have that formula. Your sum is A1 over 1 minus R for an infinite geometric series. So my first term is 72 fifths. My common ratio is 4/5. So I have 72 fifths, and I'm dividing by, looks like 1/5. There we are, dividing by fractions again. So 72/5, keep the numerator. You're going to flip the denominator and multiply. In this case, the 5s can cancel out, and so my sum is 72. I answered the second part, find the sum of it. So even for infinite geometric series, it's really about the same thing on it. You do have a starting point. Starting position is the first term, but your ending position is infinity. And you do have the expression for the infinite geometric series, which allows you to state what your ratio is. My ratio is going to be 3/4 for this one, which allows me to generate my list for the series very easily from the first term. So I have n, t of n. The first position is the one I'm starting at, n equals 1, and I'm going to count up to position 2. I'm going to go to position 3, and we're told it goes to infinity, so dot, 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 plus sign, plus sign, plus sign, dot, 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 because we're asked to list out the series, which means they're separated by plus signs. And I'm going to plug in the first term, which is 1 for n. I have 16 times 3/4 to the first power. That gives me 12. Now what I can do is I can take 12 times 3/4 on it. That's going to give me 9. And I can take 9 times 3/4 in order to generate that. And that's going to give me 27. 9 times 3 divided by 4. So there is my infinite geometric series. There's the first part. The second part says, hey, find the sum. Well, the sum is a1 over 1 minus r. I know a1 is 12, and I know my r is 3/4. So I'm going to have 12 over 1 minus 3/4. So I'm going to have 12 over 1/4. There we are again, dividing by a fraction. So I'm going to keep the numerator, and I'm going to flip and multiply for the denominator. So my sum is 48. There's the second part. Find the sum. So it's not quite as bad because you don't have to list out all the terms. You just got to realize the pattern for listing out geometric series on it is once you get the first term and you know your ratio, you multiply from that point on. So let's look at number 9. Same idea. You have your starting point. N is 1. That's good. We're going forever to infinity, and I have my expression. It's nice to analyze the expression because that allows me to see that I have a common ratio of 1/2. So once I get the first term in my list, I could then just multiply by 1/2, and that's going to give me the rest of the series. We're starting at, it says, position 1. I'm going to go to position 2, position 3, dot, dot, dot. So let's start it off. I'm going to have 144 times 1/2 to the first power. So half of 144 is 72. Remember, separating each term in a series is a plus sign. So I've asked to list out series. So that's going to be this right here. So 72. Well, now that I know my ratio is 1/2, just take half. 36. Just take half. 18. Done. It's listed out for us. And asked to find the sum. So my sum equals a1 over 1 minus r. So I have 72 over 1 minus 1/2. Well, 1 minus 1/2 is 1/2. There we are, dividing by a fraction again. So keep the numerator, flip the denominator, multiply, and I'm going to get 144 as my sum. So now, as we keep going, we can see it's actually the same thing every time. I could see from this that my base, my common ratio is 2/3. So once I get the first term in my series, I can just multiply it by 2/3, and that's going to give me my second term. I can multiply that by 2/3, it's giving me my third term, and we're just going to keep doing that because it's infinite forever. Remember, the series has plus signs separating them. All right, so let's start it out. I have 36 times 2/3 to the first power. So 36 times 2/3 is 24. And we'll do it over here. Well, what's 24 times 2/3? Well, that's 16. Well, what's 16 times 2/3? Well, that's not nice, but I have to write it as a fraction, not as a decimal. 16 times 2 is 32, and keep the thirds. So there's the first part. Write out the infinite geometric series. It's done. Now find the sum. It's a1 over 1 minus r. So my first term is 24. My ratio is 2/3. So I have 1 minus 2/3. So I have really 24 over 1/3. There we are, divided by a fraction. So flip the denominator, keep the numerator, and I'm going to get a sum of 72, which is the second part to this. So we're using that table feature, which was 8.0. I mean, that's how we started this chapter, was how to generate the table. And we're still using that concept here. And if you look at a lot of this is actually review when it comes to your formulas. You've already learned how to use the infinite geometric series formula. You've already learned how to use the regular arithmetic series formula or two geometric series formulas for finite series of those. You've learned those. You've been taught those. The new concept is how to generate your table from sigma notation. And we've learned how to deal with the table. We just now have to learn how to read sigma notation. And then we could generate our series. And once we get our series, that's no different than 8.2, no different than 8.3 for it. If you have any questions over sigma notation with the arithmetic series, geometric series, infinite geometric series, please reach out.